Okay, in this lecture, we will discuss the root locus design method. In this tutorial and the tutorials that will be followed up by this after this video, they will be discussing the design aspect of the control system using the proportional and proportional integral, proportional derivative, and then we will discuss a few of the compensators like lead lag and lag lead, and the combination of both that is known as lead lag compensator. So before going to start, let's draw a general diagram for the feedback system, feedback control system. So here we can see that we have devised a general control feedback system. In this diagram, we can see that we have an output that is fed back to the input side to compare it with the reference signal, and that will generate an error signal. Let's name it E of S. Then based upon this error signal, controller will process this input and generate the control output. So here we can see that we have make it a general representation for the controller, because we will use different kind of control based on our requirements, and we will complete the design aspect of the control system. So design aspect implies that in a root locus, let's give me another diagram. Let's assume that we have S plane, right? And we are working in a left half plane, so that we want our system to be a stable one, and based upon this stability definition, we want to operate it at a certain point in S plane. Let's assume that we are trying to obtain this operating point, that is S desired. Right. So to meet this operating point from our system, we will use the control system, and we will try different kind of controllers like proportional plus integral, proportional plus derivative controller, so that our root locus should pass through this point. And if our root will pass through this point by adjusting the gain of the controller, then we can achieve this point as a desired point. So if our controller works well, let's talk about the simplest controller, that is proportional controller, and we normally select the gain of this proportional controller as k, and if we adjust the gain as a controllable parameter, we change it. So if we are going to get the output that is passing through this point, then we can say that with certain value of gain k, we can achieve this desired point, this operating point, as the root locus will pass through this point. So root locus is nothing new to us, as root locus implies that the roots, closed loop roots, that will take some path to reach to the open loop zeros of the system with a change in the parameter, controller parameter k. The controller parameter k is the overall system gain, and it can be adjusted so that our desired point can be met with the adjustment of this gain k. So let's write a general representation of any control system. So talking about the PID control system that has all the three parameters, proportional, integral, and derivative, we can see that we have a GC of S. Let's call it the controller transfer function. It can be written as Kp plus Ki, which is the integral term, divided by S, plus Kd, which is a derivative term, and that is S. So this is a general representation of a PID control system. So this is our PID control transfer function. So from time to time, we can see that we can use it in the form of just Pi, and in this case, we will see that we have Kp plus Ki divided by S, and we have a PD of S that is equal to Kp plus Kd of S. So these are the three controllers that we are going to discuss today, and based upon our knowledge, we can see that if we write it in more general form, then we can see that it can be written as Kps plus Ki divided by S, and here we have Kp by Kd plus S whole multiplied by Kd. So why we have written these transfer functions? Because in this tutorial, we will see that when a system doesn't follow a path that is going through this desired point, you are using simple proportional gain key. Let's talk about simple proportional gain key. So in this proportional control, we can see that we have a gain equal to k, right? As this gain k has the input error signal and it has the output juice signal. So we can say that because it's a simple gain which has no sense of time, and it only acts on the present value of the error signal and produces output, control output, and that control output will be used to guide the plant towards a certain desired point. In the form of measurement, it will compare it and it will try to minimize the error. But the simple proportional gain has certain limits. We cannot set it as much high as we need, because there are certain limitations of the components or of the system. So in that case, if we are trying to achieve this desired point using this proportional controller, and the system, the root locus can have this kind of, let's assume that I take a simple example and I assume that we have changed the gain k, and root locus is following this path, and assume that it launches from here towards the open loop zeros and follows the asymptotic behavior and reaches to the infinity, which has its open loop zeros. So we can see that by the change in gain k, just proportional gain, we cannot pass through this point, right? In this case, because if these blue lines are showing that we can operate at any point with the change in gain k, because assume that k is equal to 0 at these open loop pole locations. So as we are going to increase the gain, we can have a new value of closed loop pole, and assume that for the sake of understanding, we have k equal to 10, k equal to 10, we have new operating points. So we can operate our control system on these 2 points also. So as we are going to increase the gain k, that will follow this path, this blue path, and on this path, any point on which we want to operate, we can have a real value of the gain k. So in our daily life, we can design a practical hardware where we can have this kind of performance. So this is a typical example which shows that a simple proportional controller may not work for you in this scenario, because our desired point is a bit shifted, and as compared to the root locus, and the desired point is at different location. So what we have to do, we have to change the root locus, and in this case, we can accommodate our PI or PD controller so that we can introduce a new pole, a new zero, or for a PI controller, we can expect a new pole and a new zero, right? So similarly, for the PD controller, we can see that a new zero is incorporated to achieve the desired response. So the reason for writing this kind of transfer function is that we're trying to show that when we are not able to achieve the controller performance using the just proportional controller, we can rearrange our transfer function for the controller as KP, SPI or PD or PID. So in these scenarios, we can see that we are adding additional poles and zeros into the system. By addition of poles and zeros into the system, the root locus may change. So by virtue of this whole scenario, we will be able to design a control system to achieve our desired performance. So let's start our tutorial. This was a basic introduction, and we will take one example at a time, and we will follow the controller, and then we will progress into the next example. So let's start our controls, and we are assuming that with a simple proportional controller that we normally use in the design process of the simple root locus, where we are trying to observe the pattern of the roots, closed loop roots, as they are following the some path towards open loop zeros. So we are assuming that, as we shown in the last example, that our desired point was not able to, we were not able to achieve the desired point, and so now we have to change our specifications of the control, and we will have a look onto the example where we will be having certain kind of design specifications. So in that case, we need to observe the system performance and system design. So there are different ways to design the exact desired point. But we have to start from somewhere. So in this scenario, I will follow a simple method that I will draw a diagram. So now in this example, we can see that we have a desired point SD on the S-plane. So in this S-plane, our desired point is SD, and it has certain magnitude on the real axis, and it has a certain magnitude on the j omega axis. Okay? So in this case, we have a real part and we have an imaginary part. So real part, as we know that it has a real part of any pole, it has the real contribution of minus zeta omega n, where minus shows that it is a left half plane value, and zeta omega n is the real part of the complex root that we normally know that. So we also know that. So from the earlier chapter number 4 in this book, we know that the real part has a direct contribution towards the time constant, indirect contribution towards the time constant of the system. So we can say that it has a tau is the time constant for the system, and it has a negative relation, an inverse relationship with the real part of the complex pole. Similarly, we know that cos theta is equal to damping ratio factor, right? Or we can say that theta is equal to cos inverse of zeta. So by following this, we can see that here we have a magnitude B, its vertical contribution, and we have its natural frequency omega n. So based upon this trigonometry, we can see that tan theta is equal to B by zeta omega n, or we can say that B is equal to zeta omega n into tan of theta. So our desired point now here is SD, which is based upon this whole trigonometric properties. It comes out to be minus zeta omega n, which implies that it has a negative real part, and it has a plus JB. In case if we want this desired point to be here, it will be minus JB. Obviously, it will come out to be as a consequence of our equations. So we have to meet this desired point using our controller. So starting from the simple control theory, we will consider an example and to find the controller gain that is required to be set to achieve this point SD. So example, I will follow my notes for this example. So here you can see that a simple example is that we have a system Here in this example, we have used a simple control system. We have a plant which has 3 roots, 3 poles for it in a transfer function. One is placed at the origin, other one is placed at -2, and third one is placed at -5. So drawing this one into the S-plane. So these poles are the open loop poles, and as we say that these are open loop poles, it means we are not talking about the closed loop configuration, or we can say also that for these systems in a closed loop system even the gain is equal to 0. So we are not operating any kind of control activity in this kind of configuration. So the key thing is, in this example, that we have been asked to first sketch the root locus for this system just using the proportional gain, and we have to search for the point that is critical point in this case. So by virtue of just MATLAB command, I can just have a sketch of this root locus, and it comes out to be like this one. As gain will increase, this pole will approach to its 0, that lies on the infinity. So these poles will come closer to each other as the gain will increase, and then they will depart at certain angle which is not 90 degree as we discussed in the previous case. In the previous case, there was no third pole, so we have only 2 poles, and that is why it goes to a negative and positive infinity. But here we have a third pole, and we have no 0 in the system, so all the zeros are in the infinity, so they all will behave asymptotically, right? And now in this case, we have been asked to find the critical point, and this critical point is this point, right? So by following, I'm not going to follow the steps of root locus because this is a separate part of this from this tutorial. So this is the critical point, and I will just like to add the values for this critical point, and that is S1. Let's call it S1, and it is minus 0.88, right? So these are the this is the critical point, and as this is the critical point, we have a zeta which is equal to 1. Now now in this case, so S1 which is equal to minus 0.88 is our critical point, unless it has a damping ratio equal to 1, right? So it's our critical point. Right. So the next thing that is asked in this question is you have to find the time constant, and we already know that time constant has an inverse relation with the real part of the complex pole. So we have in this example, in this case, we have S1 which has a only real contribution. So here we will write 0.88. We are going to take only absolute values because it is a function of time. We are calculating time for this thing, and it comes out to be 1.136 seconds. Similarly, following the earlier method of the root locus, we can find the magnitude of the gain k that will have the contribution to of n to the system that will help the system to reach at this critical point, means how the poles will reach at this point. So there is no zero into the in this system, so we can just calculate the vector length of this and this pole towards this zero, and I will just write the k, which is the gain that is required by the system to reach at this critical point, equal to 0.8804 multiplied by 1.12 into 4.11, and this comes out to be almost equal to 4. So now this is the whole exercise that we normally practice in the root locus method, right? So I'm not explaining the root locus method, but I'm using the final results and the procedure and the logic behind those steps. So I'm going to discuss only these things. So this is the gain that is required by the system in this system to reach the critical point. So it has a time constant of 1.136 at this point, and the zeta is equal to 1 at this critical point of 0.8804. Now again in this example, we have been asked to find the draw a line which has a damping ratio of 0.707. So in this case, the damping ratio line of 0.707 is like this one, right? So it cuts the root locus of the proportional gain at this point, right? So this is our point number 2, right? Let's call it S2. And as I'm just sketching it, so I will try to write the values that came out from the root locus command of the MATLAB. So I'm using this value, which is exact value. So though in the graph you may not be able to correlate it, as I'm not sketch it perfectly. So but I will try to write the exact values plus j, because it has an imaginary part 0.8, right? So this is our point S2, where S2 is a point on the root locus where zeta is equal to 0.707, right? So obviously it is not critical point, but it is underdamped point, right? So if you can find the time constant here, and it comes out to be 1 by real part of this, because this is real part, so we can write absolute value of this real part here, and this is equal to 1.24 seconds, right? So similarly, following the same procedure for the calculation of gain k, it is equal to 1. It implies that the contribution of each pole onto this point, we can calculate it using the vector length, and it is equal to 1 into 1.44 into 4.3, and this is equal to 7.06 second gain. So getting the summary of this whole page is that we have a plant which has a pole at origin, pole at -2 and -5. We can see that in the S-plane. And this example we have discussed 2 parts of it. First one is this one, second one is this one. In the first part, it has been asked to us to calculate the value of S1 when it is critical damp system, or alternatively we can say that it has a damping ratio of equal to 1, right? So if we are going to find this point, which is a critical point, then we have to find the time constant and the gain k that is required to achieve this point. Okay, following the similar approach, the question is asked to find the location of the desired point S2 that is on the root locus, but it is cutting the root locus at 0.707 damping ratio line, right? So this line, we have drawn this line, and this is the point which is 0.84 plus j 0.8. This is our point when zeta is equal to 0.707. Again, following the same procedure, we have find the time constant, right? And this is the gain. This is the gain. And following these two methods, we are able to progress in this way. So till this point, everything is fine. If we want to operate at this point, we can do just simple gain of simple 4 value, and we will reach at this point. And if we want to operate at this S2, there is a simple mechanism, same mechanism that we followed in the earlier case. And if we compute 7.06 value, then we can say that we are able to operate our system on this S2 desired point. But now, actual question that has been asked to us is we have to design a PD controller, right? So if in the question, if it is not mentioned that we have to design the PD controller, then we can conclude the result using the ask criteria, like if someone has asked to improve the transient performance of the system, like overshoot, setting time, time constant, rise time, peak time, like these things. So then we will try to use the PD controller. Otherwise, if someone has asked you to control the actual error, the steady state error in the system, then in that case we can use the PI controller. But for this instance, we have been asked to in a statement that you have to use the PD controller to achieve a certain desired performance. So let's talk about that desired performance. So what is that? We have been asked to design a GC, which is a controller transfer function. This one, right? So this is GC. Let me write it in this way. So now we have been asked to design a GC of S so that it has a transfer function of the PD compensator. It means we are going to design a PD compensator like this one, or writing it more generalized form, and we can say that KD into S plus this one. And the design specification is that we have to arrange the dominant poles. Dominant poles are those poles that are near to the j omega axis that will play their critical role in the performance of the system. So damping ratio should be equal to 0.707, and time constant should be equal to 0.5 seconds. Okay, now let us compare it with our previous root locus method that we have used here. So now, if we can see that for this 0.707 line, we were having 1.24 seconds of the time constant. So this is different. So if we are going to just use the proportional controller, we can achieve this zeta of 0.707 as we can see that here. But at this value of S2, which is desired point, though the zeta is equal to 0.707, but the time constant is equal to 1.24 seconds. Here, now the specifications are different. Zeta is kept same. Okay, it should have the same radial line, but root locus should be like that a time constant should be equal to 0.5 second when this radial line will cut this root locus. So in this scenario, it is impossible, right? In this scenario, in this just proportional network, it is impossible to achieve this kind of response. So what we have to do, we have to incorporate certain additional pole or zero into the system so that our root locus should shift, right? So if our radial line will cut the new root locus, then obviously it will have the damping ratio 0.7 and it will have the time constant of 0.5 second, because in that scenario we will have a look at the gain k. If it comes out to be a real gain, then we can say that it has a real gain, so we can achieve that in the practical systems, right? So let's start our system, and initially we have to find the desired point also. right? So in this case, we can see that we have a pole at origin, which is the open loop pole. We have a pole at -2 and -5 as compared to this previous example. So we have to now compute the desired point. So what is desired point? Desired point is ST. Let's call it ST. And ST should have some real part, and it should have some imaginary part, right? So following the same procedure that we did here, this one, I'm going to use calculate the desired specification for this desired point for these specifications. For these desired specification, our desired point at this point, and we will have to map this here. So first of all, calculate the zeta omega n. Zeta omega n, as we know that it has an inverse relationship with the time constant, and as the time constant is provided to us, so we can say that 1 by 0.5 and it is equal to 2. So this is the real contribution of this ST, right? So I can write it here, it is -2 plus, now we are trying to find the B, right? So B is unknown at this instance. So B, as we did earlier, that theta is equal to cos inverse of zeta, which is again provided to us, and it is equal to 0.707. So cos inverse of 0.707, and here it is equal to 45 degree. So after this, now B is equal to zeta omega n into tan of theta. It is equal to 2 multiplied by tan of 45 degree, and it comes out to be equal to 2. So it implies that our desired point is -2 plus j times 2. Okay? So this is our desired point. We want our system to operate from this desired point. So again, if I will refer to this case, we at most the point we are getting we can get is S2, which is equal to -8.84 plus j.84. This is for here zeta was equal to 0.707, but what was time constant? It was equal to 1.24. But our new desired point is here, -2 plus j2, right here. And at this desired point, we have zeta equal to 0.77, and we have a time constant of 0.5 seconds. So by simple proportional controller, which was passing like here, now we are not able to achieve this point, right? So this point is here, or we can say that this point is desired point is here. So root locus is passing from here in the proportional gain, but we want our root locus to shift towards this desired point, right? We have to shift our root locus that was earlier passing. Let me draw it a simple, very light diagram like this one, like this thing. We want to shift this root locus towards left, right? So that it should pass through this desired point, like this one. So for this purpose, we will use the definition of PD controller, which implies that we have to incorporate a GC of S, and this is nothing but it's KD into S plus, let's call it Z naught or ZC, you can whatever name you want to call it. Okay, ZC, and then we call it ZC. So ZC is our desired 0. We can say that this is 0 of the controller. So we have to arrange it somewhere in this S plane so that root locus should shift to the left half plane. So randomly, you can place it anywhere because we can readjust based upon our calculation. So for the instant, let's call it ZC. Okay, I'm placing it here. This is ZC. Again, I'm saying that I'm assuming this position. You can assume it anywhere in the S plane, because at the final, when we will calculate the values, we will see that it may change on the real plane. So following the earlier methods of computation of the angle criteria, we can see that angle criteria is the angle contributions. Okay, let me write it here. Let me draw a line here. Okay, so what angle criteria tells us that we have zeros where we don't have any 0 here. So we have ZC, which is compensator 0 only, minus, because the poles are in the denominator, so they will sum out to be in the numerator, we can say that theta pi, where I is equal to 1 to n, should be equal to minus 180 degrees. So this is the angle criteria. So here in this scenario, theta z c, which is the angle of this compensator 0 towards this desired point. So this is one of the angle, this is another angle, this is another angle, and this is another angle, right? So we have to compute these all angles. Let's say this is one of the angle, this is obviously it looks like to be 90 degree. So this is the angle of theta z naught that we are trying to find, and this is angle that of third pole. This is, let's call it theta p1, this is theta p2, and this is theta p3. So angle criteria implies that we have angles of 135 degree for theta p1, then we have angle of 90 degree for theta p2, and then we have an angle of 33.6 degree for the theta p3. Right, so here these angles are calculated using the simple formula, like I will make it 10 where y2 and y1 is the y coordinates of this desired point and this pole, and x2 and x1 are the respective desired point x-axis contribution and the pole's x-axis contribution. So as we know the location of this pole and this desired point, similarly this pole and this desired point, this pole and this desired point, so we can use this formula to compute these angles. So only thing that is left is now theta z naught. So by following this simple method equal to minus 180 degree, we can write theta zc is equal to 78.6 degrees. So now if we draw a trigonometry like this way, so I will just use this part of this diagram here. So we can see that we have a vertical point towards this pole that is lies at -2. We have a hypotenuse with a 0 zc. So this angle theta z naught is unknown to us. We know that we have display. So this point, this contribution between real axis contribution between the pole and this point is unknown to us. That is, let's call it x, and we know that the desired point imaginary axis contribution is 2, right? So magnitude wise, I'm writing the magnitude instead of real and geometric axis contribution. So we can see that by following the tan theta, you can see that it is 2 by x, or simply we can write x is equal to 2, x is equal to 2 times tan of theta, where theta is this angle. So because we are talking about ZC, okay, let's call it ZC here. So now here x is equal to 2 times tan of 78.6 degree. So this comes out to be equal to 0.4. So x is equal to 0.4, right? Okay, I will just now take a pause and I will discuss the earlier basically the base that we were describing, that initially we placed it here. Okay, this is my choice, you can place it here, anywhere in the S-plane, rail axis, on the rail axis, because as I mentioned earlier that with the calculations you will be able to precisely define the location of this 0 on this rail axis. So first we calculated the angle theta z naught, and this comes out to be 78.6 degree. So keeping this thing into mind that we are taking this reference point desired point as a reference point. So 78.6 degree implies that this 0 has the contribution of 78.6 degrees for this point, this desired point. Now we know that this is less than, obviously this is less than 90 degree, right? So if it is less than 90 degree, this is our, now if the desired point would be here like this, then this is equal to 90 degree, right? But this desired point is less than 90 degrees, so we have to place it compared to this axis. Let's call it axis that will cut the real axis for this desired point, right? This is point. So we have to place the 0 either to the left, or either to the left or the right of this perpendicular line that is cutting the real axis for this desired point. We have to place it either on the right or the left of it. So based upon the value of the angle that we obtained, we are now in a position to place it on these two sides. So the obvious choice is left side. Why? Because this 78.6 degree is less than 90 degree. Assuming that if it is equal to 178 degrees, so obviously we have to place it here, right here, like this way. So that implies that our new angle will be greater than 90 degree, right? So this is 90 degrees this point, and 178.6 degree maybe at this point, right? So now we have a pole 0 which has a 78.6 degree contribution for this point. Obviously this is less than 90 degree, so we cannot place it here, we cannot place it here. We have to search an angle that should be like this one, and for this angle we have to place it on the left side of this perpendicular line that is cutting the real axis for this desired point. So otherwise, if we choose this point here, obviously when we would be able to calculate this 78.6 degree, so we have to shift it here. So earlier we shifted it here, so we don't need to remodel the things. So now this is 0, this is pole, and this is our desired point, x is 0.4. So so it implies that our desired point is what it is. It is equal to, if we are talking about ZC absolute, this comes out to be 2.4, right? It implies this is -2, this is okay, you may call it -2 for this reason, but we are talking about the absolute value. So +2 plus 0.4, which is x, so it is equal to 2.4. So this is our ZC magnitude on the real axis. So we got the angle, we got the magnitude. So now we have to find what is ZC. ZC, as we discussed earlier, that it has a relationship like what we can see it here, that it is equal to Kp by Kd is equal to ZC. So this implies that why we were discussing absolute, because in the next step here we are now talking about the gains, so that's why we took the absolute nature of this pole 0. So Kp by Kd is equal to Zc, right? So this is our contribution for this 0. So in the next slide we will discussing the gains. What would be the gains that will be required to us to achieve this desired point. So if these gains would be real after the calculation, then we can say that we are definitely passing through this desired point. So let's calculate it. So now our new compensated system, which is nothing but it is Gc into G, which is a Planck transfer function, which we wrote it earlier, is equal to Kd into S plus 2.4, and from where we are writing it, we can see that this is Kd into S plus Kp by Kd, where Kp by Kd is the location of the 0. 2.4 multiplied by 1 by S into S plus 2 into S plus 5. So now this is our closed overall compensated transfer function for the system. So now we have to find the gain that is required to achieve this desired point, these desired specifications. If those gains would be real, it implies that the root locus will pass through the desired point with this kind of controller. So again, following the magnitude criteria that we normally use in the root locus design, that implies the contribution of each pole and 0 towards that desired point. And in that case, if we use this system and we compute the magnitude criteria, that from this one we got Kd is equal to, because this will be cross multiplying terms, and root 8, then we have 2, then we have root of 13 divided by the contribution of the lone compensator 0. Again, the magnitude criteria implies that the magnitude condition, which is nothing but it is equal to y2 minus y1 whole square plus x2 minus x1 whole square. So this is our magnitude of any point. Okay, these y1 and x2 and x1 have the same definition that we used in the earlier angle criteria. Right. So based upon this, we the KD comes out to be equal to 10. This is it implies that overall gain of the system is 10, right? Compensator gain. So specifically following the KP, we know that KP by KD is equal to 2.4 as we calculated earlier here. So as we got the value of KD, so KP will be equal to 24, which is cross multiplying the KD with the 2.4. So we can see that this value is real, this value is real. So both KP and KD are real. So overall transfer function for the controller, which is PD, is equal to 24 plus 10s, right? So this implies that whole system is basically following the process that helps us to achieve the desired point. And the proof of this concept is that the gains are real. The KP and KD both are real. If for certain reason this can happen, that your gains are not real, that then it implies that we have to change the controller. Then we have to move to maybe we have to move towards the PID control theory. So in that case, we will introduce a new pole and zero into the system, and that may help us to achieve our desired point. But for this instance, now we concluded here with the gain of KP equal to 24, KD equal to 10, with the transfer function, compensator transfer function of KD into S plus 2.4 divided by S into S plus 2 into S plus 5. What we can achieve? We have achieved a damping ratio of 0.707 and time constant at this trading line is 0.5 seconds. So this is one way to find the desired point. So you can find it with a number of times. Sometimes you may be asked to find the desired point based upon the reduced overshoot, reduced settling time, reduced peak time, rise time. All the transient specification could be given to you, and you have to find the desired point. So the fact is that there will be no incomplete information. You should have the complete information to find the desired point. So this is the whole exercise regarding the proportional constraints, and then the helping of the system with the PD controller to achieve certain desired specifications. In the next tutorial, we will going to decide under what conditions we are going to use the PI controller. So procedure remains same, but the location of the pole and zero may change, right? So hopefully you would be able to understand these things on your own also. And in case of any questions, you can ask in the comments. Till next video, take care of yourself.